Another component of free energy that we work with at the general chemistry level is the idea of entropy. Now, entropy is represented by the letter S. Now, entropy is generally defined as the disorder of a system. And while that's an acceptable answer, you'll typically see that given on tests and homeworks, it's not actually a very accurate representation of what goes on with entropy. Entropy is really defined as the degrees of freedom of a system. So, let's say you decide that you want to put 9 people together in a room and you're all going to go out to dinner together. And all 10 of you are going to go to the same restaurant. Well, how easy is it to get 10 people to the same place? Not very easy, is it? Because you've got 10 people that will have 10 different wants and desires. There's a lot of constraints put on, especially if you have a vegetarian or a vegan in the group. Now, let's say I split you into 2 groups of 5. Does it get easier? Of course, right? Now, instead of having to satisfy all 10 wants at once, you've only got little groups of 5 that only have to satisfy their 5 wants and desires. And as your groups get smaller and smaller and smaller, it gets easier and easier. Well, this is this idea of degrees of freedom. When we increase the entropy of a system, we give a lot more options and mobility to the individual atoms. So if we look at something going from like a solid to a liquid melting, that has the effect of increasing entropy because we're no longer constrained to the crystals of a solid. We have a liquid, so there's a bit of disorder or mobility associated with each of the individual molecules. And when we go from a liquid to a gas, we have even more entropy because we're no longer constrained to the volume of the liquid. We can expand to take up the whole volume of the container. Now, S is actually very small. And typically when we have an entropy value or a delta entropy value, its units are in units of joules per mole Kelvin. Now compare this to something like delta H. Delta H is in kilojoules. It's a very large amount of entropy, or a very large amount of energy, whereas delta S is in joules. It's a very teeny tiny number. On top of that, it's got a per unit of Kelvin in it. So we can't add H and S together until we multiply the entropy by the temperature. Typical values of delta S, though, depending on whether you've got a positive or negative change in entropy, somewhere between 25 and 600 joules per mole Kelvin. And again, this is plus or minus depending on whether or not you're increasing or decreasing entropy. Now, intuit that every system wants to maximize its degrees of freedom. It doesn't want to put the constraints on the atom. So if we want a reaction to be favorable, what we would prefer to have is a delta S greater than 0. And this is going to be in contrast to delta H. If we want to make the reaction more favorable, we want the delta H to be negative. For delta S, we want this to be positive. Now, there are plenty of reactions where delta S is less than 0. Freezing is an example of this. We can definitely freeze water just fine. But when we do a delta S less than 0, we are inherently making the reaction less favorable, particularly when we go to high temperatures, because we have a T delta S term in our free energy expressions. But this is it for entropy. This is your disorder or degrees of freedom component that goes into calculating the free energy of a system.